Hello everyone, my name is Supratik and I will be presenting our work Subpixel Back Projection Network for Lightweight Single Image Super Resolution. Just to give a brief introduction about super resolution, it is the process for upscaling a given low resolution image with a desired scaling factor, where the given low resolution image is the corrupted version of its corresponding high resolution image with an unknown downsampling kernel. For standard benchmarking, we know the downsampling kernel since we usually use the bicubic function to downscale an image. Super resolution is a highly posed problem. As we can see in the example, for a single low resolution image, there can be multiple high resolution solutions. Super resolution is an important classical low-level computer vision problem since it has its application in many domains, some of which are listed here. This work is heavily influenced by the last point, that is its application in gaming, especially in real-time rendering. Just to give an outline on how the presentation will follow, I'll be talking about the motivation of this research in support to some limitations in the literature. Subsequently explaining the proposed network architecture, that is the subpixel back projection network, in brief, along with the reasoning behind certain design decisions. Finally, I will give an overview of our results and conclude. As stated before, one of the main reasons behind this research was an interest in the application of super resolution in gaming and real-time rendering. Given the current trends in gaming for rendering on high-resolution displays with a consistent 60+ frame rate target, it is getting taxing for the GPUs to keep up with this. With the introduction of ray tracing in real-time rendering with the new RTX GPUs, rendering high-resolution images become more difficult. NVIDIA introduced DLSS, which stands for Deep Learning Supersampling, which is a proprietary super resolution network. The games are rendered at a lower resolution and upscaled using a custom trained model for each game using the tensor cores. This enables the games to render at higher frame rates as the computational cost on the shader cores are reduced. Exploring the literature, we can find many work on super resolution. Most of them make use of very deep networks which achieve high reconstruction accuracy but are computationally expensive. We observed that there was little work in literature focusing on shallow or lightweight networks compared to very deep networks. Given these findings, we want to focus on the real-world use cases of super resolution network by finding a balance between reconstruction accuracy and computational complexity. We wanted to study a lightweight shallow architecture which would be at par with our network without the networks of its kind in terms of reconstruction quality but more efficient in terms of execution. The NVIDIA DLSS performs a maximum of 2x upscale to achieve the best visual quality. This is the reason why we limit our study to only 2x performance of the network. Similar to other models in literature like the SRCN, DBPN, SRFBN, we also adopt a 3-layer architecture, where the first layer is a feature extraction layer, followed by a nonlinear layer and a reconstruction layer. Unlike DBPN, where they use deconvolution in back projection, we instead use subpixel convolutions. The reasoning behind this decision and how it is different from DBPN is explained ahead. We also use a global skip connection for residual learning, where instead of learning to reconstruct the entire image from the given low resolution image, we only focus on learning the residual image, that is the difference between the target image and the bicubic upscale image. In this work, we present 3 variants of our proposed network, that is the SVBP-S, M, L, that is the small, medium, and large based on their respective parameter counts. Before explaining the details of subpixel back projection block, I would like to briefly introduce the concept of iterative back projection used in image super resolution, specifically in deep back projection network. The idea is to take the low resolution input image and upscale it to have an initial super resolved image using a deconvolution or transpose convolution. We then take this super resolved image and downsample it using a strided convolution layer. Using this estimated low resolution image, we take the difference with the input low resolution image. This gives us a residual image which is then upsampled using another deconvolution layer which is then added with the initial super resolved image to form the new super resolved image. This is then fed to the down projection block. The primary idea behind the up and down projection block is to not only generate the high resolution features, but also to capture the image degradation process by projecting back to the low resolution space to understand the mutual relationship between low resolution and high resolution image to achieve better reconstruction quality. Keeping the idea of iterative back projection in mind, we used a simplified structure of back projection as seen in DBPN to reduce the computational cost. The subpixel back projection block consists of several groups of up and down sampling layers. These groups are split in two units, the exterior and the interior unit. The exterior unit comprises a single group, while the interior unit comprises 10 groups which are densely connected, similar to as in DBPN. Each group has an upsampling unit, which is a subpixel convolution layer, followed by a downsampling unit, which is a strided convolution layer. The efficient subpixel convolution was first introduced by Shai et al., where instead of convolving in the high resolution space, they convolve in the low resolution space. The deconvolution or the transpose convolution works in the high resolution space. So if we equate the computational complexity of two networks which operate in high resolution space and the low resolution space, we can see that the number of parameters for the networks operating in the low resolution space is greater than that in the high resolution space. So if we look at the equations in the slide, the ones to the left basically are the computational complexity. So one on the top left is the complexity of the network operating in low resolution space, and the one on the bottom left is the one operating in the high resolution space. Correspondingly to the right, we can see the network parameters for the corresponding low resolution and high resolution space. So over here we can see that the network operating in the low resolution space has greater number of parameters compared to the network operating in the high resolution space. To validate this idea, we tried a small experiment where we trained two models, which are SPBPS and a variant of it using deconvolution instead of subpixel convolution. These models were trained using the BSDS100 database and validated on the set5 dataset over 100 epochs. We observed that the variant using the deconvolution has a lot fewer parameters than the one using subpixel convolution at the same computational cost. This shows with the reconstruction accuracy that using the subpixel convolution gives us better results compared to the deconvolution. The network has been trained using the DIV2K dataset for 1000 epochs. We take 40 random crops of size 48 cross 48 from each of the 800 images to train the model. We use data augmentation techniques like random flipping and rotations. It was also observed that bigger crop patches result in higher PSNR SSIM. Since bigger patches also take more time to train, we stuck with 48 cross 48 patch size. Here we can see a detailed comparison of the model's performance in terms of PSNR SSIM with other state-of-the-art methods. We compared the computational complexity using the multi-adds or the floating point operation of a model. Floating point operations are computed for a 720p image with 3 channels. We can see that SPBPL and SPBPL Plus outperform all other models in the table. We can observe that CARN, IDN, FLSR are some other models which have their parameters or computational cost close to SPBPL. SPBPL Plus is the SPBPL model which uses a common technique used in super resolution called self-ensemble during inference to maximize the potential performance of the model. We can also see that among the 3 networks which have less than 30,000 parameters, namely the FSR-CNN, ESPCN and SPBPS, our proposed SPBPS model significantly outperforms the other 2 models and also is the smallest model of the 3. The same can be better visualized in these charts, where we can see how the SPBPL model has a very good trade-off between reconstruction accuracy and the computational cost, each represented in the y and x-axis respectively. The size of each bubble represents the number of parameters in each model. As explained previously, we can see the cluster forming around SPBPL with CARN, IDN, and FLSR, where we can see that SPBPL shows superior performance. Likewise, we see with SPBPS, FSRCNN, and ESPCN that the SPBPS outperforms the other two tiny networks for all four datasets. In 2x, it can be very difficult to distinctively see the difference between super resolved images. I'm not sure how clear it will be over this presentation, but a general comment would be most of the visuals are at par, which was the initial objective, that is to find an efficient network at par with state-of-the-art reconstruction performance. In conclusion, we presented a novel network architecture for single image super resolution. We have been able to demonstrate good trade-off between reconstruction accuracy and computational cost. We can further explore replacing the DenseNet with ResNet, which might help with optimizing the memory usage. The source code for the same is also available on GitHub. With this, I conclude my presentation. Thank you.